This video discusses writing radicals in simplest form using properties of rational exponents. It includes adding and subtracting radicals, and it goes over questions 9 through 18 on your review, although there is some weird numbering going on, so there's actually a few more or a few less questions depending on which way you look at it. All right, so let's get started. Number 9 is the fifth root of 1,215. When you are simplifying radicals, you're going to be looking at the index. It's going to be a really important number. So since we're looking at fifth root, we are thinking of perfect fifths. Your perfect fifths are 32, 243, 1,024, and 3,125. So we're going to use those numbers and try to find one that goes into, or that 1,215 is divisible by. So if we start dividing, we find that 243, which is a perfect fifth, times 5 equals 1,215. So we do that because we can take the fifth root of 243, which is 3. This is left over. It's stuck in jail, so it stays behind. So that would be our answer on 9. So you find your perfect fifth that goes into 1,215, and you rewrite it, and then you take the fifth root. Number 10, you're going to do the same thing, but first we have to do something else. We see that these things are being multiplied, so we're going to multiply what's on the outside, and then we're also going to multiply what's on the inside. And then we're going to simplify using perfect cubes this time. The perfect cube that goes into 135 is 27, and it's 27 times 5. So I'm going to take the cube root of 27, which is 3, and multiply it by that number that's already on the outside. So 3 times 6 is 18. So in case you didn't catch that, I took the cube root of 27, which is 3, and I multiplied it by 6 and got 18. Number 11, we have properties of exponents. We have a power of a power. Anytime we have a power of a power like that, we keep the base and we multiply our powers. 2 fifths times 1/3 is 2 over 15. I can't do anything else to simplify. I have no other x's to combine it with. There's nothing else I can do, so that's my final answer. On number 10, we're also using properties of exponents. When you have two things that have the same base and you're multiplying, you add your powers. 5 halves plus 1 half is 6 halves, which can be rewritten as 3. So 7 cubed would be our final answer. 14 is the fourth root of a bunch of stuff on the inside. Remember, anytime we're rewriting radicals, we're going to start by rewriting it as two different fourth things. This is going to be our perfect fourth bracket, our perfect fourth radical. And the second one is going to be our leftover, our stuck in jail, stuff that's not going to change. So first thing I need to do is find my perfect fourth that goes into 64, and it's 16. So I put that in my perfect fourth radical, and it's times 4 to equal 64. So the 4 goes in the leftover. Then in my perfect fourth radical, I have to have x's, y's, and z's raised to a power that's a multiple of 4, since 4 is my index. So I'm thinking about my multiples of 4. I have 4, 8, 12, 16. I want the biggest one that's still less than 6, because that's how many x's I have in my original problem. So I can only have 4 x's in my perfect radical. And then I have 2 left over because I have to have a total of 6. With my y's, I can also only have 4 y's with 3 leftovers. They have to total 7. The one in the perfect fourth radical has to be a multiple of 4 and has to be less than 7. With my z's, I have 8 of those. 8 is already a multiple of 4, so I'm just going to put all of those in my perfect fourth radical and none of my leftovers. After I've done that, after I've separated them into the two, I'm going to actually take the fourth root of all of this. The fourth root of 16 is 2. The fourth root of x to the fourth, I'm just going to take my power 4 and I'm going to divide it by my index. So I'll have a power of 1 on x. Same thing with y. 4 divided by 4 is 1. On z, 8 divided by 4 is 2, so I'll have z squared. And then my leftover stuff isn't changing at all. It just stays exactly like it is. So that's kind of a longer problem. 15 is a little bit shorter. Remember when we take the square root, it's the same as raising something to the 1/2 power. And so I like to rewrite mine like this because it's just easier for me to see. And now it's kind of like the problem that we did on number 11. We have a power of a power, so we multiply those powers. 3/7 times 1/2 is 3/14. And that's all we can do on that one. 16, we're adding radical expressions. We can see that our erradicands are the exact same, and as are our indices. So we're just going to add the coefficients. We have 15 cube root of 4. I don't have a perfect cube that 4 is divisible by, so I can't simplify this, so that's my answer. On 17, we're looking at square roots, but our radicands are different. I have the square root of 3 and the square root of 27. So I have to check to see if there's any perfect squares that go into either of those to see if I can simplify. There's no perfect square that goes into 3, so that's going to stay the same. However, 27 can be rewritten as the square root of 9 times the square root of 3. The square root of 9 is 3 times negative 5 is negative 15. So I can rewrite negative 5 root 27 as negative 15 root 3. Now they have the same radicands, so I just can add the numbers in front and get negative 11 square root of 3. Last problem, very similar to 17. I'm going to simplify both the square root of 32 and the square root of 50. Square root of 32 can be rewritten as square root of 16 times 2. And square root of 50 can be rewritten as square root of 25 times 2. Square root of 16 is 4 times 7 is 28, so 28 root 2. Square root of 25 is 5 times 4 is 20, so 20 root 2. I have the same radicands. Now I can add my numbers in front, and I get 8 square root of 2. There's a lot of different things covered in this objective, so if I were you, I would look at the extra practice and go over some more of those. Thank you.